back to Techno Churchy, where we speak about tech and the church, and you have the power. First and foremost, let me thank you for always supporting this channel, for always dropping by just to drop a comment, to say you are learning, just to drop a like, or just to share, or even subscribe. If you don't subscribe, please subscribe, because we are hoping to continue this for a very, very long time. Okay? If you're locked in, say inside. Inside. I'm in an electrifying mood this day. Why? Because we're going to talk about current. But it's not, if you're looking for, if you thought we're going to talk about current news, I'm sorry, this is the wrong channel. You can try KBC YouTube channel. You know what KBC means. But I'm here to talk about current, and when we're talking about current, what we are doing is we are talking about what? Electricity. Okay? From an engineering perspective, when we talk about current, we tend to complicate things. You hear people talking about electrons and positively charged electrons, negatively charged electrons, electrons flowing from the negative side to the positive side. It is too much. Too much. Oh, I don't know sine waves, I don't know sine whatever. Too much. Let us simplify it. And to understand current, first of all, the most basic way, or the least tiring way to understand it is to look at current, voltage, and what's the other one? And resistance as water flowing through a pipe. Okay? Where the pressure of the water, as we had said in the Ohm's law, remember the last lesson when we were talking about Ohm's law, the water pressure is the voltage, the water flowing through the pipe is the current, and the size of the pipe is the resistance. Okay? So you even remember a recap of the Ohm's law, where voltage was current times resistance. You remember that? So you remember even we tried to define what Ohm's law was, and now we are here. Today I just thought we needed to speak about current and understand current much more, understand why we call some current AC, some current DC, and why some home appliances cannot use DC but use AC while others use DC, why transmission of electricity, supply of power in the home is done in AC and not DC. You get? So those are some of the things we are going to look at when you're dealing with current. And then in the next video, we will do parallel and series connections. If you love electricity, zap me, zip. Electrify me, zip. You are electrified. You feel it? You feel the electricity in the house? You feel the electricity. There's a lot of electricity in the house. I can feel it. I hope you can also feel it. Okay, what's the difference between DC and AC? DC simply stands for direct current. It simply means that current flows in one direction. We know that current flows from the negative side to the positive side, all right? That is, when it comes to polarity, it flows from the negative side to the positive side. And in a DC current circuit, current flows in one direction. That is, it flows from negative to positive, and that does not change throughout the polarity. Does not change throughout as long as the connection is still on, is still working, the circuit is still closed. Okay, but then we have this AC that alternates, hence the name alternating current, meaning it keeps changing direction. For an AC, the polarity keeps changing. At one point it's positive, the next moment it's negative. And the best way for us to understand that is using a graph. So we'll move to my whiteboard, my amazing whiteboard here, so that I can do a demonstration. Is that cool? Cool. So we've spoken about current, right? It's spoken about DC and AC. And we've said DC is direct current. And AC is alternating current. All right. In a closed circuit, a graphic representation of DC will look something like this. On the y-axis, we have voltage. On the x-axis, we have time. So you realize that over time, you realize that for a direct current, as long as the flow of the voltage is consistent, you realize that the current is steady. Current flows in one direction and it streams in one direction, and it does not change direction. It does not alternate direction. Okay, but now in reality, because most of the time the battery or whatever source you are using tends to lose voltage drops, you realize that it will look something like this. This is the reality. This is the for learning purposes. For in real sense, it might look like a curve, because over time the source of the power loses energy, unless it's a DC generator, which is not everyone can afford. But most of the time we use batteries to supply DC power, and this is what happens. Okay, but now when we come to the alternating current, you realize that the graph changes. Instead of having an L-shaped graph, I don't know how to explain that without saying the L. The graph looks more like this. It's like a T that is lying on its head. That makes sense. So you realize that when we are starting, this is voltage and this is time. As we begin, you realize that the voltage will begin from moving like this. Then, because it's alternating, it will come down and make something like that. Then again, the same, repeat. It keeps repeating. Just know that. Yes, I've run out of whiteboard, but just know that it keeps repeating that cycle. So you realize that it is alternating from, at one moment it was positive, then it comes negative. You know how a graph is plotted. You know that this is 0, positive, negative. You get? Yeah. So a whole complete alternation like this is called a cycle. Okay? And the measure of cycle in the measure of amount of cycles per second is what we refer to as frequency. Okay? So frequency is simply measured in any wave. You remember, even in audio, you'll understand that we deal with waves, and this type of wave is called sinusoidal wave, right? So in a sinusoidal wave, you realize that that's a cycle, and so the measure of amount of cycles per second is what we call frequency of a wave, or frequency of a current in this situation. Okay, and current and frequency is measured in hertz. If you remember from what? From waves in audio is the same. Okay, so sometimes in your appliance or device, you will see it's written AC, sorry, it's written AC 50 or 60 hertz. Okay, that simply means this is the standard that a country uses when it comes to AC power. Okay, a good number of devices that use AC power use this standard. One of them is the electrical bulb. I think I have a bulb here. This is a normal bulb, normal household bulb. It uses AC power, and most of the time you'll realize, yeah, like, I don't know if you can see. Let me come closer to the camera so you can see. Is it visible? Yeah, you see it's written AC 50/60 hertz. Okay, meaning that's the amount of cycles per second that that bulb can handle. All right. Now, when we switch on the light bulb, that same alternation happens. Only that our eyes are too slow that cannot see that the alternation, the change in polarity in power. You get? So if you see this, or back to the wave, see this. If it is slowed down to a level that the eyes can see, you realize that when the current is positive, the power goes, the bulb will light. Let's take for example, it's a bulb we are lighting. When the current is positive, the bulb goes brighter. Then when it is negative, the bulb goes dimmer, brighter, dimmer. I don't know if you've ever seen, even when you're doing a shoot. I don't know if you've ever seen, even when you're doing a shoot and you are recording a screen, a TV screen, and you realize that there are these lines on the TV screen. Okay? The best way to deal with that is to change the settings on your camera to match the frequency of the recommended frequency standard, the recommended AC frequency standards for your country. Okay? We've seen the graphical representation of both DC and AC. So from these two, we can derive, or rather, is what was used to derive the symbols for AC and DC, so that when you see them in an electrical diagram, you don't confuse them. Okay, so in an electrical diagram, or even on your charger or your adapter, you will see for DC the symbol is something like this. So it has simply been derived from this. Okay, so if you see this, just know that this thing is powered using DC. So you don't need to push AC, because if you put AC, you might blow your equipment. Okay, for DC, it's simply, usually they use a simple cycle like that. Sometimes they cross it like this. Sorry. Sometimes they close it like this, but most of the time you will find that it's just represented like that, a simple cycle like that. Now, since we've explained what AC and DC is, you wonder, then what is the fuss about? Why is it that sometimes we get to use AC and sometimes we get to use DC? Why can't we just use AC or why can't we use DC if DC is stable? Why can't we use AC, especially in things like the bulb and among other things? Why can't we just use what? DC and not AC? Or why can't we just supply power to the homes using DC and forget about AC? For that, we must go back in time. history books tell us about two of the greatest, arguably the greatest, the greatest inventors of our recent past, and that is Thomas Edison and Nikola Tesla. These two guys were great inventors, from telecommunication to media to electricity. They were pushing boundaries. They were pushing limits. They were pushing boundaries, and I must admit that we as humanity, we were blessed to have the two. Because if it weren't for the two, even the cameras that we are using, possibly we will not be using them like we are using now. Most of the machines we are using, we will not be using them like we are using them now. Even the radio that you listen to, these two people had contribution to those, and among other things. Okay. Now, where did it all start? It starts when Edison invented the light bulb, and so because Edison was not just an inventor, he did not just have a technical mind, he also had a business mind. He was a capitalist as well, and so for him, anything he invented meant it needed to bring money for him, and so he marketed the bulb, and then he realized that he needed to supply power to homes because the homes didn't have power, and so he came up with a DC generator to supply power to homes. And so for the first few homes, things were working well, but then he realized that there was voltage drop, and people who are 2 kilometers away from the power generating station could not enjoy the power. And so he needed a solution, and the solution he came up with was to build power plants in every 2 kilometers, so that anyone within the 2 kilometer radius was able to get power. But you see, the setback with this is that imagine a world where every 2 kilometers you have a power generating plant. Just imagine that. Number one, it is space consuming, it is not easy to build these plants, and it is very, very expensive. So at that time, I think Tesla had just joined Edison in Edison's company. Tesla was wait, where did Tesla come from? Wait, no, he was not Bulgarian, he was not Croat. Was he Bulgarian? Can't remember. One of those countries that are near Russia. So when Tesla came and joined Edison, Edison gave Tesla a challenge. Told Tesla, if you can improve my DC generator, I will give you this amount of money. And Tesla was a genius. This guy was brilliant. So for a few months, he worked onto this project, and he came up with a few modifications, and he was able to modify that generator. But Edison did not keep his end of the bargain, because he was to pay him certain money, and so with that, Tesla left Edison, and so Tesla went ahead and because of that, he was able to modify these generators, and that's when he came up with the AC power. And so when Edison realized that Tesla had come up with the AC generating power generate a way to generate AC power, and the advantages that AC had over DC was that with AC you could supply it for long distances without dropping voltage, and also you could step down or step up voltage as much as almost at will, and it was simpler to build to do that by simply building mounting transformers in every the same concept we are still using till today, instead of as compared to the DC system where you had to build a whole plant. With AC, you only had to build the transformers, which are mechanical devices that are easier to operate compared to the DC power plants. And so Edison, noticing this, he realized that he might lose work, because now he had generators and these generators would not sell, and he was chasing deals, big deals that would mean he would be miles ahead in terms of business. So what happens? Edison goes on a campaign to to do what? To bring down Tesla and his AC power. But he even goes to an extent where he invents equipment to electrocute animals to demonstrate to people that AC power is dangerous. The negative side of AC power is that it was dangerous. True. AC power is more dangerous than DC. But Edison's approach was not, his intention was not really to demonstrate to people that AC was more dangerous than DC, but rather to kill DC, to kill AC, so that his DC systems could sell. Okay? Now, because Edison had gone to an extreme, Tesla also went to an extreme. He came up with a way to prove to people that AC power was, in as much as it was dangerous, it could still be used safely. He came up with a way of passing AC electrical current through his body without him being electrocuted. Don't even try to imagine that. It was crazy. It was crazy. And so, in the end, the general public was convinced that AC could be used. But then you ask yourself, if AC could be used, why are we still having DC? Yeah, if it seems as if Tesla won, why are we still having the Edison's DC? you get? Number one, we need to look at the advantages and the applications of AC and DC. The advantages of AC, as I mentioned, first of all, is that AC, you can, there's no line drop. By line drop, I mean when between one point of supply to another, you don't get voltage drop in between. That is the advantage of AC. What I simply mean in a layman's language is that you can send AC power for long distance without losing so much voltage. You can send high voltage, let me put it even better. You can send high voltage AC power with low current, you get what I'm saying, without losing voltage. The second advantage of AC is that you can step it up or step it down at different stages to fit different purposes. For example, for an industry, you'll probably take 415 volts. For a home supply, you'll do somewhere between 110 to 40 volts. So you always keep changing. But for DC, it is very difficult to do that. For DC, it is very difficult. So those are the advantages that AC had over DC. And that's why it was easier for Tesla to supply power in those days, even for us now. You get? So that is why AC is used mostly for distribution, from power plant, power generating companies, from power generating plants to the last consumer, which is at the home. But then you realize that when the moment the AC power gets to the house, not every appliance, not every equipment in the house will use AC. Of course, the light bulb that I just demonstrated to you uses AC. We have AC generators. We have some, what else uses AC? What else uses AC? Some heating elements, cookers, they use AC. But now when you come to appliances or electronics that have complex circuit boards, you realize that we now move to DC. Why? Because DC is more stable, and by nature, these appliances require stability, especially for appliances that have some processing. You get, especially for electronics. That's why your laptop has to change AC power to DC. You realize it is rated input, it is rated The adapter input is rated 120 to 240 volts most of the time, and then you see the output is written something like 12 volts DC, and you wonder why. It is because most electronic devices require clean power. Okay, even your phone, that's why you have to charge your phone. You can't just plug your phone directly into the socket and use it the way you'd use a bulb. We don't charge bulbs. Of course, nowadays there are bulbs that store power, but generally we don't charge them. All right? So those are the advantages and the applications of AC and DC. So what is the bottom line? The bottom line is that at the end of the day, both Edison and Tesla won. There was no outright winner. You would say, oh, but Edison, Tesla, yes, Tesla might have won the supply battle, but Edison won the application battle. So it still works to our advantage, and that is why I'm usually very grateful, very, very grateful. For more of that, you can check out, you can Google the War of Currents. It's all over the internet and all over history. It's an amazing document. The amazing documentaries of these two gentlemen who are amazing. As a matter of fact, they're some of the two scientists or two inventors that I regard so highly as a person. All right. So, is there anything I've left? Yeah, I've covered a bit of history. I've covered a bit of history. I've covered a bit of differences between AC and DC. I've given you the definitions. I've given you the applications and advantages. Okay? Otherwise, from me, I think that's it. As I usually say, you'll be blessed because you came. As I promised, in the next video, we'll be handling parallel and versus series circuits. We'll be handling more about voltage. I don't know if we might look at Cauchy's law a bit. Probably. I'll do a little research on that and see if we can talk about it a bit. Okay? From me, I'm glad you came. If you've not subscribed, please subscribe. Please subscribe. I'm on road to 200 subscribers. I'm past 100. I won't sing that song anymore. To 200. So as we are moving on to 200 subscribers, please subscribe. I can't get there without you. So you know that. So you know you are the one who has the power. You have the power. I'm here to talk about technology and church. But the power comes from you. You have to subscribe, my friend. If you don't subscribe, please subscribe. Otherwise, let me get out of here before I zap more power into you. All right? Cool, man. I'm out.